let's do a couple of more rotational volume problems, and I'm going to make these a little bit more difficult. And hopefully, after these, if you've understood everything we've done up to now and the ones I'm about to do, I think you're pretty set for most of what you should face in most math classes, and definitely I think you'll be set for the AP exam in either AB or BC on this concept. So let's do another example. Okay, so let's say that I want to actually let me do something different. Let me draw it here because so that's my y-axis. This is my x-axis. Now let me draw the function y is equal to x squared. So let's say this is y is equal to x squared. And we know that that could be written as y is equal to x squared, or we could write that as x is equal to square root of y, depending on what we want to be a function of what. Right? This is the y-axis. This is the x-axis. Let's say I also have the line y equals, I don't know, y equals, let's say this is the line y equals 2. It goes over what I just wrote. Y equals 2. Now, this problem is going to be slightly different than what we've done so far. So let's say I'm going to take a rotation, but instead of taking a rotation around the y or the x-axis, I'm going to take a rotation around another line. So let's say I want to take a rotation of, let me pick the area. Let me say between x is equal to 0. Say x is equal to, actually let me do something arbitrary. Let me say between x is equal to 1, so that's that point, and x is equal to 2, that's where they intersect. Right? This is the point right here. This is 2, 2, 2, comma 2. Oh, sorry, no, 2, comma 4, because y is equal to x squared. So this is 2, comma 4. This is the point 4. So what I want, and what point is this? This is the point 1. Right? So our y values go from 4 to 1, our x values go from 1 to 2. And that makes sense because y is x squared. And so if we were to kind of take the area that we're going to rotate, and haven't told you what we're going to rotate it around yet, and this might prove to be shocking to you. So this is the area we're going to rotate. Instead of rotating it around the y-axis, I want to rotate it around the line y is equal to minus 2. So I want to, so if that's 2, y equals minus 2 should be roughly here. So I'm going to rotate this area, and around this line. Around this line. So what's that going to look like? It's going to be a fairly big ring. Like if I were to try to draw it, let me see if I can even make an attempt. Once again, this is always the hardest part, just drawing what I'm trying to rotate. I'll try to do it from an upward perspective. So that's kind of the inner loop, and then there'll be an outer loop. The top is flat, right? Because it's defined by y is equal to 4, so that's the top. The top is flat. And the inside is also going to be a hard edge, right? So the inside is also going to be a hard edge like that. But then the outside is going to curve inward. I don't know if you can, if you see what I'm saying, because this is the outside. It's curving inward. So it's a ring. It's going to be a big ring. And so if I were to draw the axis, this would be the y-axis coming in. No, sorry. Whoops. Edit, undo. The y-axis is actually going to be closer to this hand side, right? The y-axis is going to be in the middle of kind of the, so this is going to be the y-axis coming up here, right? That's going to be the y-axis. And then the x-axis is going to come below that. I'm drawing everything at an angle as best as I can. The x-axis is going to come below that. And then this line, we're rotating it around. That's going to be someplace over here. That's going to be the, whoops. That's going to be something like that. It's going to go behind there and come back over there. Hopefully that makes sense. We're just getting a big ring. So how are we going to do this? Well, I think the easiest thing to do, well, actually, there's a couple of things we can do. First, we could just use the shell method using the x value. So how do we do that? The important thing is to always visualize the shell or the disk. So in the shell method, we're going to take slivers like this, right? Where the width of that sliver is dx. I could draw it really big. So that's like the rectangle is going to be dx. The height, what's the height going to be of this sliver? Well, it's going to be the top function minus the bottom function. It's going to be y equals 4 minus x squared, right? So this is going to be 4 minus x squared, the height at any point right here. And then if I were to do the shell, just like we did before, let me see if I can draw a decent shell. I think I'm getting better at this. Let's see, and then this is one edge of the shell. That's the other shell. We already figured out that the width of the shell is dx. The height is 4 minus x squared, right? The top function minus the bottom function. That tells you the distance between the two. And then what's the radius going to be? What's the radius of that shell going to be? Well, is it going to be just x? Is it just going to be the x value? No, the x value would tell you the distance from the y-axis to that shell. And it's going to be from minus 2 to the x value. So it's going to be essentially 2 plus x, right? That's going to be the radius at any point. And this is where we diverge from what we've done before. Before, the radius was just x, but now it's 2 plus x. So what's the circumference of each shell going to be? Well, circumference is equal to 2 pi r, and our radius is 2 plus x. So it's 2 pi times 2 plus x, which equals 4 pi plus 4 pi plus 2 pi x. That's the circumference. And then what's the surface area of this? Well, it's going to be the circumference times the height. So surface area, I'll write that area surface is equal to that, the circumference. 4 pi plus 2 pi x, all of that times the height, times 4 minus x squared. And let's see if we can FOIL this out or distribute this out. So 4 pi times 4 is 16 pi. 4 pi minus x squared minus 4 pi x squared. 2 pi x times 4 plus 8 pi x, and then 2 pi x times minus x squared. So that's minus 2 pi x to the third. So that's the surface area of each ring. And then if we want the volume of each shell, essentially, we multiply it times the width, the dx. dx. And then if we want, so that's the volume of each shell, and if we want the volume of all the shells, we sum them up. We sum them up. So we take the integral. That's an integral sign. I'm running out of space like I always do. And where do I take the integral from? I take the integral from x is equal to 1 to x is equal to 2. From 1 to 2. That's probably too small for you to read. 1 to 2. So let's see if we can take the antiderivative of this. Let me make some space free just so I don't have to write so small. So I'll keep this down here because that's the setup of the problem. And I think I can get rid of a lot of this. I think that is pretty good. Okay, and let me switch to another color. And we're ready to take the antiderivative. So what's the antiderivative of this? So the antiderivative of 16 pi is 16 pi x, 16 pi x. And then what's the antiderivative of 4 pi x squared? Well, it's going to be x to the third over 3, so it'll be minus 4 pi over 3. Sorry, 4 pi over 3 x to the third. And then we have plus, well, this will be x squared over 2, so it'll be plus 4 pi x squared. And then minus, this will be x to the fourth over 4, so minus pi over 2, just divided by 4. X to the fourth. I'm going to evaluate that. This is a much hairier problem than what we've been doing at 2 and at 1. So what is it evaluated at 2? It is 32 pi minus 4 pi over 3 times 8 plus 4 pi times 4 plus 16 pi minus, what's this? 2 to the fourth is 16 divided by 2 minus 8 pi. And then I just realized I'm running out of time, so I will continue this in the next video.